Pipeline hazards. There are situations in pipelining when the next instruction cannot execute in the following clock cycle. These events are called hazards, and there are three different types that are structure hazards, data hazards, and control hazards. Number one, structure hazard when a pipeline instruction cannot execute in the proper clock cycle because the hardware does not support the combination of instructions that are set to execute. This first hazard is called a structure hazards. So it means that the hardware cannot support the combination of instructions that we want to execute in the same clock cycle. A structural hazard is uh, the less annoying for the designers. So the LEG V8 instruction set was designed to be pipelines, making it fairly easy for a designer to avoid structural hazards when designing a pipeline. Let's suppose, however, that we had a single memory instead of two memories. If the pipeline had a fourth instruction, we would see that in the same clock cycle, the first instruction is accessing data from memory while the fourth instruction is fetching an instruction from the same memory. Without two memories, our pipeline could have a structural hazards. In summary, uh, we see that in a load instruction or in a store instruction, we need to read and write data from the memory. But if we try to read and write data in the same time in the same memory, then a structural hazard occurs because we cannot read on the same memory uh, at the same time. uh, we can only read or write that memory. Uh, so if we have a single memory, then structural hazards occurs. And if we want to avoid the structural hazard, we need separate memories for reading and writing our instruction sets. Data hazards, also called pipeline data hazards, when a plant instruction cannot execute in the proper clock cycle because data that are needed to execute the instructions are not yet available. So the data hazard occurs when the pipeline must be stalled because one step must wait for another to complete. In a computer pipeline, data hazard arises from the dependency of one instruction on an earlier one that is still in the pipeline. For example, suppose we have an add instructions followed by immediately by a subtract instruction that uses uh, the if, for example, we have add x19 x0 x1 sub x2 x19 x3. We see that add and sub uses the same register x19. So the second instruction sub cannot execute until the add instruction completes execution, because when we want to execute sub instruction, then it did not have the proper data in the x19 register, because in pipelining these add and subtract instructions uh, execute simultaneously at the same time. So when the sub instructions uh, want to read register X19, then add instructions is still in execution and did not write its data in into the X19 registers. So without intervention, a data hazard could severely stall the pipeline. The add instruction does not write its results until the fifth stage, meaning that we would have to waste 3 clock cycles in the pipelining. Although we could try to rely on compilers to remove all such hazards, the results would not be satisfactory. This dependency happens just too often and the delay is far too long to accept the compiler to rescue us from this situation. There are some solutions for this for the data hazards. Number one is forwarding. Forwarding, also called bypassing, a method of resolving a data hazard by retrieving the missing data element from internal buffers rather than waiting for it to arrive from programmer visible register or the memory. So the primary solution is based on the observation that we do not need to wait for the instruction to complete before trying to resolve the data hazard. For the code sequence above, add and subtract, as soon as the ALU creates the sum for the add, we can supply it as an input for this subtract instruction, adding extra hardware to retrieve the missing item early from the internal resources. This is called forwarding or bypassing. This figure shows the connections to forward the values in X1 after the execution stage of the add instruction as input to the execution stage of the subtraction instruction. In this graphical representation of events, forwarding paths are valid only if the destination stage is later in time than the store stage. For example, there cannot be a valid forwarding path from the output of the memory access stage in the first instruction to input of the execution stage of the following, since that would mean going backward in time. Forwarding works very well. It cannot prevent all pipeline stalls, however. As we see in the previous slide, forwarding works very well. Although it cannot always avoid stalls for forwarding. For example, suppose if the first instruction was a load of x1 instead of an add instructions, then the desired data would be available only after the fourth stage of the first instruction in the dependency, which is too late for the input of the third stage of a subtraction instruction. Hence, even with forwarding, we would have to stall one stage of a load use data hazards. The following figure shows an important pipeline concept, officially called a pipeline stall, but often given the nickname bubble. A pipeline stall, also called bubble, is a stall initiated in order to resolve a hazards. How to avoid pipeline stalls? Let's consider a C language code that is A is equal to B plus E and C is equal to B plus F. When we convert this C language code into LEGV8 code, uh, we have the following LEGV8 code, that is load x1 x0 hash 0, load x2 x0 hash 8, then add x3 x1 x2, store x3 x0 hash 24, load x4 x0 hash 16, then add x5 x1 x4, then store x5 x0 hash 32. So what are the hazards in this preceding code segment, and how to uh, reorder the instructions to avoid any pipelining hazard or stalls in this piece of code. When we see the code on the left hand side of this picture, we see that the both add instructions has hazards because of their respective dependency on the previous load instructions. For example, the first add needs data eh, from the register x2, but it is not available until the load instructions completes written above this add instruction. Similarly, in the second add instructions, data needed in x4 register is not available until the load uh, instructions executed written above this add instructions. So this takes total 13 clock cycles to complete this instructions set. On the other hand, there is a solution that how to avoid these stalls in pipelines. Uh, the solution is very similar. If we simply move the third load instructions to the and move it to upward and write it on the third position of the code, then we see that the both hazards removes. So on the pipeline processor, we're forwarding the reordered sequence will complete in 2 fewer cycles than the original one, and the code completes in 11 clock cycles instead of 13 clock cycles. The third hazards is a control hazards. Control hazards, also called branch hazards, when the proper instruction cannot execute in the proper pipeline clock cycle because the instruction that was fetched is not the one that is needed. That is, the flow of instruction addresses is not what the pipeline expected. So the third type of hazards is a control hazard arising from the need to make a decision based on the result of one instruction while other are executing. As we see that while executing the instructions one by one, the program counter always fetches the next instructions which is going to be execute in the following clock cycle. So uh, being fetching the instructions following the branch on the following clock cycle, the pipeline cannot possibly knows what the next instruction should be, since it only just received the branch instruction from memory. Just as one possible solution is to stall immediately after we fetch a branch, waiting until the pipeline determines the outcome of the branch and knows what instruction addresses to fetch from. For example, that we put an enough extra hardware so that we can test a register, calculate the branch address, and update the PC during the second stage of the pipeline. To avoid such hazards, it is possible to insert one or more stalls into the pipeline, which delays the execution of the current instruction until the required operand is written to the register file. This decreases pipeline efficiency and throughput, which is contrary to the goals of pipeline process design. Stalls are an expedient method of loss restore that can be used when compiler actions or forwarding fail or might not be supported in hardware or software design. For example, in this figure, we assume the conditional branch is taken and the instruction at the destination of the branch is the OR instruction. There is a one stage pipeline stall or bubble after the branch instruction. In reality, the process of creating a stall is slightly more complicated, so it affects on the performance of the pipelining. However, the performance is the same as would occur if a bubble were inserted. The branch prediction. Branch prediction is the ability to make an educated guess about which way a branch will go. Will the branch be taken or not? In the predict not taken approach, treat every branch is not taken. Remember that the registers are read during ID, and we also perform an equality test to decide whether to branch or not. We simply load in the next instruction, which is PC plus 4, and continue. The complexity arises when the branch evaluates to be true and we end up needing to actually taking the branch. In such a case, the pipeline is cleared of any code loaded from the not taken path and the execution continues. In the predict taken approach, we assume that the branch is always taken. This method will work for processors that have the target address computed in time for the instruction fetch stage of the next instruction, so there is no delay, and the condition alone may not be evaluated. This will not work for the LEGV8 architecture with the 5-stage pipeline. Hence, the branch target is computed during the ID cycle or later, and the condition is also evaluated in the same clock cycle. Uh, Prediction that branches are not taken as a solution to control hazards. In this diagram shows the pipeline when the branch is not taken. The top diagram shows when the branch is not taken, and the bottom diagram shows the pipeline when the branch is taken. As we noted, the insertion of a bubble in this fashion simplifies what actually happens, at least during the first clock cycle immediately following the branch. More realistic branch prediction. Uh, Branch prediction strategies. Some ideas for branch outcome prediction, as static branch prediction and dynamic branch prediction. In the static branch prediction, static branch means that the prediction is the same every time a branch is fetched. There are three levels of static branch prediction strategies. Number one, always taken or always not taken. Uh, in this strategy, every branch is predicted to go a particular way. Implementing an always not taken strategy is the simplest thing to do, since it eliminates the need of target prediction. Instructions are fetched and speculatively executed down the non-taken path. The accuracy of this technique is low, however, it can be improved with compiler cooperation. Number two, static uh, branch prediction. For, uh, for instance, a particular strategy is backward taken or forward not taken. Backward branches are assumed to be loop back edges that are frequently taken, while forward branches are assumed to be frequently not taken. This strategy is more accurate. Number three, strategy of static branch prediction. This is hint bits in the instruction set architecture. Some instruction set architectures allow conditional branch instruction to include hint bits that let the architecture know which direction the branch is likely to be taken. These hint bits can be set through smart compiler. Uh, this technique achieves about 90% accuracy. Number two is the dynamic branch prediction. Every time a branch is executed, a machine algorithm or the hardware gives a prediction for the branch. Dynamic branch prediction can predict branches that static branches prediction cannot. For example, loopback edges with fixed trip counts. Uh, There are some types of dynamic branch prediction. Number one is biomodel predictions. It is a table of bits indexed by branch. PC mean program counter is kept. Each time a branch executes, the corresponding bit is set to 1 if the branch was taken and set to 0 if branch is not taken. The next time the branch needs to be predicted, the corresponding bit is taken as the prediction. This is like the hint bit in the instruction set architecture for static prediction, but the hint bits are learned online without a separate proofing run. Note that the system will predict highly based branches well, but for instance, a loopback edge with the low trip counts will be mispredicted twice. Once at the loop exit and once the very next time the back edge is encountered. Number two, dynamic prediction. It is instead of keeping a table of bits, we keep a table of 2-bit counters that saturate a 3 and 0. When a branch is taken, the corresponding counter is incremented. When the branch is not taken, the counter is decremented. When a branch needs to be predicted, the high bit of the corresponding counter is taken as the prediction. The lower bit provides hysteresis, take into account the history of the branch beyond just the last time the branch was executed. So a loopback edge will ensure only on misprediction at a loop exit. Pipelining. Pipelining increases the number of simultaneously executing instructions and the rate at which instructions are started and completed. Pipelining does not reduce the time it takes to complete an individual instruction, also called the latency. For example, the 5-stage pipeline still takes 5 clock cycles for the instructions to complete. So pipelining improves instruction throughput rather than individual instruction execution time. Instructions set can either make life harder or similar for pipeline designers who must already cope with structural control and data hazards. Branch prediction and forwarding help make a computer fast while still getting